Hello and welcome to another LeetCode video. Today we're going to be working on soup servings. In this problem there's two types of soup, A and B, and we have n milliliters of each type of soup, and there's four kinds of operations. We can either serve 100 milliliters of A as 0B, 100A, 25B, or sorry, 75A, 25B, 50-50, or 25A and 75B. When we serve some soup, we give it to someone we no longer have it. On each turn we will choose one of the four operations at random. And if the volume of soup is not enough to complete the operation, we'll serve as much as possible. We'll stop when we have no longer a quantity of both types of soup. And note that we do not have an operation where 100 mLs are used first. Return the probability that soup A will be empty first, plus half the probability that A and B will become empty at the same time. Answers within 10 to the fifth of the actual answer will be accepted. So I will start off by saying this problem is, if you get asked this on an interview, I would say it's close to impossible to solve, and there's just like a trick you need to kind of know. And then if you do know it, then it becomes kind of easy. So I'm not a huge fan of this problem, as you can see, it has a ton of downvotes. I think when I first solved it today, I think it had like 900. So pretty much everyone's downvoting this problem because it's not the best problem. But it is a good problem once you know the trick. So let's go through the trick. So essentially, what we're going to do, and we can look at the first example. So they're asking, like, what's the probability that this is the case for the first example? And so if you think about it, there's a 50% chance that A just wins straight up, right? Like if you do 1 and 2 and you only have 50, if you do 1 or 2, then you will have served all of A. So there's a 50% chance that you serve A first. And then for the second one, there's a 25% chance that A and B are tied. So that's another, so this will be like 25% times, I think it'll be like 50 or something. But essentially, so here it is here. So it's 25%. So basically when A wins, the probability is 1. But then when it's tied, you only get half because it's a half. So the way you would do this is you would say, okay, if it's A or B, A wins straight up. So we'll just say 1 plus 1 plus a half plus 0. I'll go into this more. I don't think this example is great either. But essentially, this would be, there's a 25% chance of each of these happening. So it would be this. And I know it's a little bit confusing, and I'll get into that. But I think there's just a better way of explaining this problem that we're going to get into. So here's what the problem basically boils down to. So let's just look at the average amount of soup we're serving, right? So we can serve 100 milliliters, we can serve 75, 50, or 25. And so we're actually gonna, because this is in 25s, we're actually gonna say that instead of doing it in 25s, we'll just do it in terms of, we're just gonna divide everything by 25 to start off, and then that'll make things easier for us to work with, right? So let's do that first. So let's just divide everything by 25 to start off. So we'll just say we can either serve 4 servings, we can serve 3 servings, we can serve 2 servings or 1 serving of A. And then for B, we can serve 0, 1, 2, or 3. So the average amount served for A here is 4 plus 6, and then it's over 4, right? So it's like 10 over 4. So we're serving on average 2.5 servings of A, and if you wanted to multiply this by 25, it would be like 62.5. And of B, we're serving 6 over 10, right? Sorry, 6 over 4. Yeah, 6 over 4. Because the probability of each one of these is quarter. So of B, you're actually only serving 1.5 servings. So essentially, you're serving 2.5 servings of A on average, and 1.5 of B. And basically the trick to this problem is that actually when you have things like this, it's like the same kind of thing as like if you flip a coin and the chance of heads is like 60% and the chance of B is 40% or something, it would be phrased like, what are the chances of A winning or there being a tie? So the chances of there being a tie are pretty small, but the chances of A winning are pretty good to start off, but they're not 100%. But as this number gets really, really big, like as this number gets into the thousands, this probability pretty much goes to 1. And so that's the same thing for this problem, is if we're serving 2.5 servings for A, and we're serving 1.5 servings for B, we're serving way more of A, right? Like we're serving, this is like, if you think about it, this is 4 total. So this would be like This would be like 2.5 out of 4 for A. So essentially, we're going to be serving something like 5 out of 8, right, for A, which is 62.5%. So we're serving 62.5% for A versus 37.5 for B. And because we're serving more A than B, once the number of total like of these random attempts goes up big enough due to the law of large numbers, what happens is this becomes very close to the number that you're actually going to be serving. So the chances of running out of A is going to be pretty much 100% once the number gets big enough. And so that's a trick to solving this problem is, even though when you first look at it, you're like, wow, my constraints are huge. It's 10 to the 9th. I can't do any DP. I can't even do linear, right? Like, it's just way too big. Like, even a linear, can I do some logarithmic? And the answer is no. And that's where this problem is really dumb, because you have to recognize that you only need to solve it for a small constraint, because for anything bigger, it will just approach 1, right? So if you're n, so I actually did, and what you can do is you can actually run a DP, and I'll show you later. And I think once n is like 3,700 or so, then you're pretty much getting 1 here. And so you only have to solve, your constraints are actually 3,700 or less, which is kind of really dumb. And so now that you know our constraint is 3,700, now let's go back and let's think about the problem, right? Now let's actually think about like, how do we solve this problem? So if our constraints are 3,700, it's pretty straightforward, right? We can do DP because we have like a perfect scenario for DP essentially, where, you know, so remember our constraint is 3,700, so let's draw that. And now let's just look at the problem one more time, and it's going to be a lot clearer. And remember, we're going to take our servings of soup, and we're going to divide by 4 just to make it easier to work with. We're going to have smaller numbers. And essentially, so let's say you have like 60 mLs of soup. How would we do that if we just divide by 4? Well, this would be 2 servings, but if you notice that, you see, I think it tells you once the volume is not enough to complete, we will serve as much as possible. And so if you have like 10 mLs, it's the same thing as having 25 mLs. You still have to have the 1 serving to actually finish serving the soup. So we can just say like, let's just divide it by 4, and if there's a remainder, let's add 1. So for example, if we have something like 60, we'll just say this is going to be 3 servings, right? It's going to be 2 full servings and 1 not full serving, but it doesn't really matter. So this is going to go to 3. Okay. So how do we actually do this? Now that we know that our parameters are not too big, right? It's like 10 to the 4th, which is totally doable with DP. And so how do we do this problem now? Well, it becomes a lot easier, right? So let's think of our DP states now, essentially, right? So we have a few DP states, and like I said, this 3,700 is actually going to be smaller because we're dividing by 25. So this 3,700 will be divided by 25, so that's going to be something like, you know, this is 10 to the 4th, which is a little shaky for DP, but because this is in terms of 25, if you divide by 25, I think it's along the lines of like 100, or I think it's around, right? Because 25 times 100 is 2,500. So it's not 100, but it's like 150. And now we got our parameters from 3,700 down to like 150, and now we have like a really easy DP, right? And so now that we have 150, how are we going to do this? So let's go through this. So let's say, you know, our n can be 150. What things do we need for DP, essentially? Now that we know, like, once our number is big enough, we just don't care. Okay, so let's figure that out. So let's think about what we need for the DP, right? So we need the parameters. Let's make some space here. Then we need a base case. And then we need a recursive case, right? So we actually need more space for the base case because there's going to be a few of them. Okay, so for the parameters, now that we got our soups down to 150, it's going to be pretty straightforward, right? We can just have soup A, the quantity of soup A, and the quantity of soup B. What's going to be our base case? So we have a few base cases. So if soup A is 0, or in our case, it can actually be less than 0, but it doesn't really matter, right? Like if we have 1 serving, we're going to subtract 4 servings each time, but essentially less than 0, it's going to mean the same as 0. So if soup A is less than or equal to 0, and soup B is less than or equal to 0, like if they're both at the same time, then what do we want to return? So we actually want to return 1/2 the probability of A and B. So we're actually going to return 1/2 here. And then if soup A is less than or equal to 0, then that means that soup A1, because we already checked if they're at the same time. So if soup A1, we're going to return 1. And then if soup B is less than or equal to 0, that means soup B1, so we're going to return 0 because we don't care about that, right? We only want the probability of soup A or soup A and soup B. So these are our base cases. And for the recursive case, it's pretty straightforward, right? Like all we have to do is we just have to think of like what kind of things can happen, right? So we're going to have something where you just have 25% chance of every single thing happening, right? So we'll just say like 25% chance and then all 4 of these DP states, all 4 of the next DP states. So we can just add those all up, right? 25% chance of one, 25% chance of the other, you know? So like for these examples, it'd be 25% chance this is the next DP state, 25% chance this is the next DP state, and so on, all of these. And then finally, we can just return. And so if you think about it, that's all we need. But yeah, the reason this problem is really shitty is because it's kind of hard to figure out this law of large numbers thing, realizing that like once your numbers are big enough, your stuff will actually just round to 1, and so you don't really care. And so now we have enough to be coding, so we have everything we need. So let's code. And so like I said, we can just say if n, I tested this before, and I will show you. If n is greater than 3700, we can just return 1. And yeah, essentially this is just like a guess and check using DP and big numbers. And like this is roughly where it becomes 1. Anything over, I mean, it's not exact, but it's somewhere close to this. Anything over this will be 1. Maybe it could be like 3600 or so on. And now this is going to simplify our parameters a ton, right? So now we could say n equals n divided by 4. And then we're actually going to add 1 if n mod 4, meaning like if we have something like, or actually this shouldn't be divided by 4, this should be 25. So if we have something like 101 milliliters, that extra 1 milliliter will still be a serving, right? We still don't have the empty soup. So 1 if n mod 25, and this is going to be, does not equal 0, right? So else 0, okay? And now what we need to do is we need to do the DP. So we can just say, and we need to visit it as well, right? So we have visited, so we can just say default div here, and then we can just have like, what's our function going to be called? We can call it like serve soup or something, right? So we'll just say def serve soup of soup A, soup B, and then now we're going to do our base cases. So if soup A is less than or equal to 0 and soup B is less than or equal to 0, then we are going to return 1. Oops. Not that. Okay, then we're going to return 1. And then if soup A, I guess technically what we could do is we could make this a little bit cleaner, right, to not. So we could say if soup A, we could say if soup B is less than or equal to 0, return. So this is going to be the tie, so we're going to return a half, else return 1. That's going to be a little bit cleaner, right? Okay, now if soup B is less than or equal to 0, we're going to return 0 because we don't care about that one. Now finally we're going to do our recursive case, so we're going to say visited, this is just going to be a one-liner, so AB is going to be 0.25 times, and then this, we're just literally going through all of these recursive cases. So the first recursive cases, we're doing 100 mLs of soup A, which is 4 servings. So we're going to say soup A minus 4, or minus 4 servings, because remember, we divided by 25, so we really have like 4 servings of soup A here. So we have soup A minus 4, then B stays the same. Now we add all these probabilities into the total, right? So we do plus 0.25. This one happens, and so for the second one, we have 3 servings of soup A, and we have 1 serving of soup B, so it's going to be soup B minus 1. And then we can add some more to it down here. So we can say this, just so we have more space. We can copy this again, essentially. So these are all the 4 states, right? Okay. And this is 0.25 times soup A minus 2, and then soup B minus 2. So this should actually be soup B here. This shouldn't be 0, right? This is essentially saying our soup B stays the same. And then for the last case, we have 25 mLs of soup A, which means we're only serving one portion. And then we have 3 portions of soup B. So hopefully that's right. Let's just double check. So this should be 4 and 0. Yes, this is incorrect. This should be 4 and 0. Then it should be 3 and 1, which is correct. Then it should be 2 and 2, which is correct. And then it should be 1 and 3, which is correct. Okay, now finally we can return this. Visited AB. Okay, and yeah, so that's everything for that. And now we also need to do return serve soup, and this needs to be n and n, right? These are the servings. Okay, there we go. Oh, we forgot one more base case actually. So our base case we actually forgot the caching base case, right? So if A, B, in visited, return visited AB. Okay. Oh, let's see. All right, this should be a soup A. So let's just copy that. So soup A. This should be soup B. And this should be soup A, soup B. Okay, let's see if that's good. DP. All right. So we called it serve soup. Let's just call it DP instead to make it easier because I use DP. Okay. Okay, and then this should be DP. So many. Oh, right. I did call it A and B. So we're actually going to do a find or replace here just to make it easier. So we're actually going to look for soup A. And we're going to replace it with A just to make it easier for us. And we're going to look for B, replace with B. There we go. Now it's a little bit cleaner. So we're using A and B for soup A and soup B. Nice little feature also in LeetCode. You can just do a find and replace of all your code. Just kind of convenient. Okay. And there we go. And so you can see it's really efficient. And so I did want to show you what this would look like. So if we actually have a custom test case for something like 3700, and we got rid of this, so I think I should be able to type it right now. Nice. And so let's actually comment this out for now, and we're going to see what this gives us. So we're actually going to do our normal DP for 3700, and you're going to see it actually returns this, which is within 10 to the negative 5 of 1. So if you just return 1 here, this will be close enough. And anything more than this is going to be, you know, like if you do 3800. So I think we have to go to test case 3800. Hopefully saves it. Okay, I think it should. Let's just double check. Let's see. Okay, so yeah, you can see for 3800 it's 0.996 and so on. And so for all these numbers, essentially, it's actually going to be close to 1. And so if you actually do take this out and you submit, you're going to get an error because you're going to have DP of some huge number, but this is essentially going to be 1. Like this isn't even going to be close. Because if we do, if we do DP of 3800, it's already almost there. And if we do DP of like 4800 or something, if we run it, you know, this is 0.9999 and so on. So it's going to get closer and closer to 1. So this is right around the point where, you know, your stuff is pretty much going to round to 1. And that makes it really efficient. So that's the trick to this problem, is just knowing this law of large numbers thing. Definitely something that I think once you get a hint in an interview, the problem becomes pretty straightforward. Because if you think about it, since this is 25, you know, if you have 10 to the 9th and you divide by 25, then you have something like 10 to the 7th, which is still like, you know, or 10 to the 8th, which is still like linear time. But we got our 3700 all the way down to like 150. And so this is 150 is like 10 squared essentially, right? And so when we have 10 squared, we can do whatever, like almost anything will pass. But yeah, so hopefully you like this problem. Definitely not a fan favorite. As you can see, it's going down and down and down. But yeah, if you like my solution, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.